Hello, today's video will be on diffraction. So what is diffraction? So diffraction, before telling you what is diffraction is one of the proofs that a light or electromagnetic wave has wave nature, not only the particle nature. So how do we know that the light has wave nature? So one of the proofs for the light is the experiment of interference that was done by Young's double slit experiment. This interference is on my other video. If you want to go through the interference again, go ahead in that video. If you're clear, then let's continue with the second proof of wave nature, that is diffraction. Now, what is diffraction? It is nothing, it's just the bending of a wave. So let's say this is a ray model of wave. So there is a ray of light coming from, let's say, the sun. So whenever this light ray meets an obstacle, so let's say it hits a slit, okay, but this slit is very small, so small that this small d here is almost equal to the wavelength of light. Okay, now the wavelength of visible light would be in the order of around, let's say, 400 nanometers. So you want the slit to be this small. So if the slit is this small, then this light ray, which is supposed to go straight, okay, would end up bending at the edge and enter where it should be completely dark. Now see, this is a kind of a slit in, let's say, a door. Okay, now if you have a screen here, what would you see on this screen? You should see a bright spot of light here, and this entire thing should be dark and this should be dark. But instead, what happens is you end up seeing some light in the dark region too. So how did this light come here? So this was the slit. My light was supposed to be going straight. So because the light has bent at the edge of this slit, I end up getting some light in the dark region. So this phenomena is called diffraction. All right, let me just explain you diffraction through sound wave. Let's say you are standing near a wall, okay, and this wall has a door here. So let's say this is the entry to a room and your friend is here. Now, because this is a wall, you cannot see your friend, okay? This is because the light ray coming from your friend is going straight, it's not reaching your eye. You can see your friend only when the light ray reaches your eye. But if your friend speaks, okay, so he's speaking, what he does is produces a sound wave. Now this sound wave ends up bending and ends up coming to you. So the sound waves clearly show diffraction because instead of traveling straight, they end up bending here and you hear the friend, but you don't see the friend, hence the light wave is not bending. So that is why for ages, for a century, for 100 years, people believe that light is not a wave. Should be a particle nature. It goes straight. But actually it was not bending because the light has a very small wavelength. And this opening is way larger than the size of the wavelength of the light. So the bending would happen even in light if the opening is of the order of the wavelength. Now this is a condition that you need to remember for your A levels too. So it was a condition for diffraction that the opening should be order of the wavelength. Now for sound wave, if you typically consider the speed of the sound is around 330 meters per second and the visible frequency is from 20 hertz to 20,000 hertz. 20,000 hertz. So if I use my calculator, this would give me, using V equals to F lambda. Okay, just so using V equals to F lambda, I get my velocity is 330 meters per second approximately, depending on the speed of the sound changes with the temperature, the day temperature and the humidity. But assuming that this is so if I take this as 20 hertz, frequency is 20 hertz times wavelength, so I get my wavelength as around 16 meters, 16.5 meters. Okay, and if I take it as 20,000 hertz, my wavelength is coming as around 0.0165 meters. So do you see how high? Have I taken enough of zeros? 1000 is 1, 2, 3. Yeah. So the wavelength, sound wave has a very high wavelength, and normally the size of your window or the door would be around what? Half a meter maximum. So it is, the wavelength of the sound waves is or the order of the daily life slits and the openings. So the sound wave bend easily. But the problem with the light wave is that the wavelength of the light is in the range of around 300 to 750 for nanometers. So it's around 300 to, let's say, roughly around 700 nanometers. This is for visible light. Now, it is very difficult to get such openings in the daily life. Your doors and windows are way bigger than that, so the light would not bend. But when we do this, as you can see on this CD, what's happening is the slits on the CD, if you see it very closely, a CD, the slits are of the order of the wavelength of light. And that is why whenever light hits at different angles to the CD, it is bending. So if you are seeing purple color, it's the purple wavelength that is bending. If you see the red color, it's the red that's bending. So different colors are bending at different angles and producing constructive interference. So just to cut it short, what is diffraction then? It is nothing but bending of light. Bending of wave, to be more precise. Bending of waves. And when does the wave bend? When the slit size is of the order of the wavelength. Now, for this, this is the formula which is very commonly seen in your A-level exams. So I'm just trying to show this diagram here. So there's a slit opening. Now this slit again has to be very, very small in size. So we produce something called as diffraction grating. So diffraction grating is when we produce around 10,000 slits in 1 millimeter or 1,000 slits in 1 millimeter. That close. So diffraction grating is when you have number of slits. Okay, slits. That's it. So diffraction grating is that's number of slits. So this small space has lots of slits. So let's say, just for the sake of our clear diagram, there is a light ray entering this and it bends. Okay, and I have a screen here and the light ray which is entering at the center going straight, and the light ray which is here is, let's say, bending and reaching here. So let's say these two light rays are reaching here and they are producing constructive interference. Now, from the video of interference, whenever the path difference is of the order of wavelength, multiple of wavelength, the interference or in the nature of the superposition would result into constructive interference. So the path difference between these two lines, I'm just going to make it again here. So this is Let me just clear this and make the diagram clear. So between this top wave, let's say I'm taking this as S1. I'm using the same letters that I use in interference, so it helps you a little bit understand more. So S1, and then this would be the path difference between the two waves S1P and S2P. So the path difference is this. And this path difference, if I take my slit size, I'm just making it here. So if I take my slit size is of small d, then d sine theta, where this is my theta. So then my d sine theta, whenever it satisfies n lambda, it is constructive interference, and I see fringes. So the central one, my n is 0. And if I put it here, let's say n equals to 1, and then n equals to 2. So the central one, n equals to 0, would be known as the central fringe. So this is the central fringe. Or the central maxima. So this is your first order, second order, third order, and so on. Now, if, let's say, for example, some of the questions, d sine theta is equals to n lambda. So if the question says, what is the maximum order of the fringe? So they want the value of n to be maximum. So if you want the value of n to be maximum, sine theta would be 1, because that's a maximum value of sine theta. So in that case, my n would be, the maximum value of n would be d over lambda. This is maximum n. Okay, so constructive interference happens whenever the path difference is n lambda. The only difference between the interference and diffraction would be that this is happening in a single slit. The Young's double slit experiment was a double slit. So this is, the waves are interfering constructively and destructively with each other from different parts in the same slit. So only thing is, in diffraction, we are not interested in destructive interference because they are not as perfect as it was in interference. In interference, all the fringes were uniform. So if you have constructive or interference and destructive interference, we had alternate dark and bright fringes, and all of them were of equal width. Whereas in diffraction, you would see a central maxima, which would be having maximum intensity. And as you go away from the center on the screen, okay, so this is the screen. If you go away from the center on the screen, the intensity would reduce considerably. And this would not be, so the dark fringes are not very, they do not follow a perfect pattern. So we do not consider dark or destructive interference in diffraction, only in Young's double slit experiment. Okay, so let's just do some questions on that. Again, pause before you hear the answer. Try to do it yourself. What is diffraction? It is, yes, you are absolutely right. It is bending or spreading of waves at an aperture or an obstacle. Provided what's the condition? It should be of the order of, okay, that's the next question. It should be nearly the gap size. Which change increases diffraction? So if I want to increase the diffraction, think of the light wave and the sound wave. How do you increase diffraction? By increasing the wavelength. So that's not right. This is right. Okay. Describe the diffraction pattern formed by the single slit. Now, we have done that. What was the kind of the diffraction pattern? So there was a central maxima. All right, try to write the answer. Pause it and write the answer, and then check. The central maxima is wide and bright. And then the secondary maximas are dimmer and narrower. So as you go away from the slit, so this is your slit and the screen. So the central, all the light is reaching here. So this is your central maxima. And as you go away from the central maxima, they becomes dimmer and dimmer. And of course narrower. So intensity decreases away from the center. Light of wavelength 600 nanometers. So I've got my wavelength. So wavelength on a grating with 500 lines per millimeter. So 1 millimeter has 500 lines. So what is D? Your D is then 1 mm divided by 500. Of course, we need to convert mm into meters. 10 to the power minus 3 divided by 500. That's my D. You have to find the angle for first order maxima. N is 1. Go ahead, do it. If you've done, check. So you calculate D first. Okay, then use the equation. N here was 1. Okay, do this one. You have wavelength. Don't forget to convert nanometers to meters. The grating spacing. Now this time, they have not given you the line. They have directly given you the value of D. Highest possible order, remember theta is 90. Okay, check. The answer is fourth order. Light passes through a diffraction grating. So this time again you will have to calculate D. This is in millimeters, so D will be 1 over 600, and this is in millimeters, so 10 to the power minus 3. So you've done this one. Okay, go ahead, pause and do it, and then check. All right, you can go ahead, pause and check your answers. So that's it. So what you need to know for today is that diffraction is just bending of the waves. As you can see in the front of this, that these lines here, again, this is from the previous video, these are wave fronts. So as you can see, as they enter a slit of suitable size, they bend. So this was straight line and they are bending. So bending of the wave is diffraction. Condition is the wavelength should be order of the slit size or of the obstacle. Thank you.